Okay, I'll begin with a word of prayer. Excuse me. I seem to have gotten a cough, so. Heavenly Father, we thank you for this day, and thank you for this class and this semester. Pray you help us to use this time wisely, and just to wrap up a quick review of the course. Lord, in your name I pray, Lord Jesus. Amen. Okay, so this is just going back down memory lane here. This is test 1, right? So these kinds of things can still be on the final. Like we started by how to calculate, this is like how to calculate the sign of something. So in order to do that effectively, I have to really put the input into the sign into its Cartesian form. And then once I do that, then I can go back to like the definition of sine. Or if you had on hand the relation between sine and sinh, you could just immediately go from this to that, you know. So I'd say like having the sine, sinh, cosh, cosine, cosh conversion formulas handy would be a smart thing to have on like a formula. Do I give you guys a formula card? What did I say? I think you guys can have, I think I can allow a page of notes for the final this time. That should be fine. I don't always, but this year. Don't tell the others. I know Violet's too busy eating at Slim Chickens today. Know about this kind of thing, but anyway, irrelevant personal comments aside, this one, oh, see, I still believe in the number 42 back at this point. So whenever you have something to like a suspiciously high power, the way to go there is to convert it into polar form, right? So the two things we started with in this course is how to like put a complex number into Cartesian form, which is a plus ib, or polar form, which is, you know, radius times e to the I standard angle. Anyway, so problem 2 is pretty standard, and you guys almost without exception ignored my hint. You may assume known properties of complex conjugation. That is the way to prove this, because you know the conjugate of, the length of z is the square root of z bar, you know, or z bar z, and so you just use that, and it's not bad. If you do this in real notation, it actually takes some calculation, you know, like it actually is a non-trivial algebra identity there if you work it out in the reals, like real notation. If you're trying to solve an exponential, the logarithm's the way to go. Like essentially by definition, if e to the 3z is equal to 1 plus I, that means 3z is an element of little log of 1 plus I. The way we calculate little log is we take the principal logarithm and then add 2 pi iz to that. So like the principal logarithm here is actually this piece and that piece, and then I've got a plus 2 pi iz. But the little log is a set of values, whereas the big log is going to be a specific value, where the different choices of logarithms are based, of course, on different choices of angle. We looked at like 4 different ways to look at differentiation in this course. The definition in terms of the difference quotient. I talked about this method of Carathéodory. Of course, we also talked about the Cauchy-Riemann equations. And last but seemingly easiest is the Wirtinger calculus, the partial z-bar business. So we had these 4 viewpoints. Here I asked you guys to look at it 2 different ways. The difference quotient, which I have here. Of course, the other way you could do difference quotient a la calculus 1 would be like the limit of z goes to z naught of f of z minus z naught over z minus z naught. Sometimes that's easier. And then like Carathéodory, basically you're just looking to figure out what the quotient function is. Like basically phi of z is the formula for the difference quotient. To actually calculate the phi of z, what I always do is take like f of z minus f of a, and then look to factor out z minus a. Whatever's the cofactor to z minus a, that's going to be the Carathéodory function. And if that thing is continuous, then it serves the role of the limit point as z approaches a is going to be the value of the derivative, which here is a plus a, which is 2a, of course. F prime of a is 2a here. So anyway, there's that. We had problems like that in the homework, of course. This was, here I give you component functions, u and v, you know, find all points where it's complex differentiable. So complex differentiable implies Cauchy-Riemann equations hold. So we just need to look for where ux is equal to vy and where ui is equal to minus vx. But that forces the equation x squared minus y equal minus y squared, which implies that y and x are equal, and they both must be 0. Yeah. So we only get the origin is the only place it's complex differentiable, which means it's nowhere holomorphic, because to be holomorphic means that you're complex differentiable not just at the point, but in like a neighborhood of the point. So if we're only complex differentiable at the origin, it's nowhere holomorphic. There's no like open set on which it's complex differentiable. We later learned that holomorphic at a point is interchangeable with analytic at the point, meaning that it has a power series that represents it. Oh, I had a choose your own adventure deal here. You can either prove the product rule or you can prove the power rule. And the z to the power c we define by, exponential of c times the principal logarithm. Since I said the context would be the split complex plane. And so that's this, and it's just basically like chain rule and properties. It's a straight calculation. The product rule I would think would have been the easier one. You can see the lecture notes for proof of that. We did it in class 2. Problem 8 was a standard, here's 1/2 of a complex differentiable function, find the other half. We call that the harmonic conjugate problem. So like, if I have a function which is harmonic, what does that mean? To say u is harmonic means that uxx plus uyy equals to 0. It solves Laplace's equation. And so it's easy enough to check that this is harmonic because uxx is 2 and uyy is minus 2, so 2 plus minus 2 is 0. So that's a harmonic function. And so you're trying to solve the Cauchy-Riemann equations to find the harmonic conjugate. So if we integrate this, we get 2xy. If we integrate that, we get like minus 4x plus 2xy. Obviously, we only need one copy of 2xy. But what I did was I integrated with respect to y this one, then I plugged that into here, which gave me this, which ends up giving me dc1 dx equals to minus 4, which of course integrates to give 4x, minus 4x. And so that's the harmonic conjugate. It's the same calculation we did in Calc 3 to find the potential energy for a conservative force, really. Yeah. It's very, very similar to that in terms of like calculus. It's not exactly that because, you got this minus that's injected in here from the Cauchy-Riemann equations, but the spirit of the calculation is that calculus 3 thing. You can always check your answer too, right? Now, of course, the other way to check the answer is to notice that if we put it back in terms of z notation, like u plus iv here is this plus that. And if you group things, you can see actually that's minus 4iz plus z squared. Well, that is only a function of z, and as such, it's complex differentiable. By the Wirtinger calculus, the partial derivative of this with respect to z bar is 0, manifestly so. Therefore, it's complex differentiable. Like that's the fastest. The fastest rule of thumb is if something is just a function of z in a polynomial sense, or if it's a composite of like a polynomial in z with one of your basic functions like sine or cosine or cosh or sinh, then it's going to be holomorphic. But showing that directly from the Cauchy-Riemann equations could actually take some work, right? Because to actually find component functions for a given complex function, it can be a lot of work. This one here was a quadratic equation, and so to solve it, we complete the square, and then we have to use the principal square root function. So if I have a problem like this, I am not content to have an answer left as a square root of a complex number. I'm interested in how that breaks down, how that simplifies. So you leave me answers on the test that are like this, unless I've explicitly said otherwise, I'm going to take points off, just so you know. Because I'm interested, part of the course is learning how to actually calculate that. So that's like plus or minus e to the pi I over 6, because, well, that's how the principal square root calculates here. Anyway, so we get these two solutions. Yeah, let's see here. This stumped everybody except for one, which was kind of funny. But yeah, apparently 42 to the 4th power is 3,111,696. And so so this is that, and then you can use the standard like pre-calculus factoring tricks to like factor it. Basically 42 squared is minus 42i squared. So it's plus 42i and minus 42i and like that. But of course, the other way to do this would be to find the principal fourth roots of 3,111,696. And when you did that, you'd find that you've got like the fourth root of the number, I times the fourth root of the number, minus the fourth root of the number, and minus I times the fourth root of the number as your zeros. So you take z minus the 0 and multiply the product of those. You can do that. All right, anyway, I think I've got 42 out of my system for now, so you're probably safe from that one on the final. This is what I was just talking about. It's actually troublesome sometimes to find the component functions of a complex function, right? But this is an important calculation in the course. One of the first things we had to, grapple with early on is how do you find the real and the imaginary component functions for a complex differentiable function, or not necessarily complex differentiable, but just for a complex valued function of a complex variable. And so like here, what I want to do is I want to make the input to the cosine like manifestly in Cartesian form, so I have a separation of like the real part and the imaginary part. And then once I get that, then the adding angles formula still holds for cosine. Like cosine of a sum is cosine of the, cosine A, cosine B minus sine A, sine B. And then past that, we're back to those cosine, cosh, sine, sinh transformation identities. That's so much of like, yeah.
So for that one, we just, because z equals x plus iy, we plugged in x plus iy for z.
Yeah.
Like
Exactly.
Z, and from there we just use would be trig identities.
Yeah, basically trig identities. So you put z, like you said, put z equal to x plus iy, and then do trig identities.
Okay.
Yeah. And ultimately, but you're done when you only have one I, and everything else is real functions. Real function, real function, real function, real function. If one of these has got an I in it, you're not done. Right? Because that's just another notation to, well, it's just not done. Problem 12 was in the homework, I think. I don't think I just sprung this to you guys on the test. Like, I think this was in the homework. Oh yeah, there's a remark. This was in the homework. And there was a lot of floundering on this problem, if I remember right. It's a hard problem. So, why is it that when the argument of z1 is equal to the argument of z2, that the length of z1 plus z2 is the length of z1 plus the length of z2. Geometrically, this is just obvious, right? Like, if they have the same argument, they're pointing in the same direction. So of course, if you add two things that are pointing in the same direction, the length of the sum is the sum of the lengths. But I want us to show that here, I guess I left an opening here. You reasonably could have drawn a picture and said the geometric proof is clear, and I would have been like, rats, he's not wrong, but fortunately you guys didn't think of that. Well, anyway, what's done is done. You guys are going to replace your score on this test with the final exam score, probably most people. I don't remember. Did anybody do well on this test? I can't remember. Somebody must have. Anyway, so the thing that makes this a little bit subtle is saying the two little arguments are equal does not make the argument equal. Like it means that, it doesn't mean that when we represent the two numbers in terms of polar coordinates, it doesn't mean that their thetas are the same. It means that their thetas differ by 2 pi multiple of integer multiple of pi. So that's what I'm dealing with here. Z1 plus Z2 is this plus this, right? But this theta 2, we can write as theta 1 plus 2 pi j. That much is this. The fact that this is related to that in this way, that's what's given to us by the arguments being equal. And of course, 2 pi j times I that's just 1, because cosine of 2 pi j is 1 and sine of 2 pi j is 0. And then we got it. Problem 13 is a line. So if we have the distance between two fixed points, we're looking at the solution set of points that have equal distance from a given pair of points. Well, that describes a line, actually. And so the line has parallel bisector of the displacement vector between the points, which you might call the focal points of the line. Like if I was to draw the line from -3 to 3i here, that would be the perpendicular bisector of the line, which is the solution set here. And of course, you can also work it out from algebra, as I do here. Square both sides, cancel out the offending squares, and do algebra, you get y equals -x. There are about well, I guess there are about like 3 or 4 different versions of this problem. This is maybe the nicest version. The other versions of this problem are like, you could have the sum, the distance from one point plus the distance to another point is equal to a constant, right? The solution set of things like that, that will give you an ellipse. If I have the distance from one point minus the distance to another point is equal to a constant, that's going to give you a hyperbola. If I have, like the distance from this point plus the distance from this point is equal to a negative number, the answer is nothing. Because you can't have the sum of positive things equal to a negative, That's kind of what happens here. Or you got the line problem. This all goes back to the study of conic sections, which most of you guys have been cheated from. You haven't had a proper treatment of conic sections in your like pre-calculus algebra days, because you'd have to have a pre-calculus algebra teacher who understood these things, and likelihood of you having such a teacher is low, because we graduate people who don't know anything these days. so, not us so much, but all the other schools, of course. But sorry. This one is a backwards differentiation problem. This is like a sneaky backwards reverse magic trick kind of problem. The point here is that this limit, you don't want to calculate directly because it's horrible. If you were to break that up into it's like what it means in terms of reals, it's deplorable, it's bad. But on the other hand, if you tilt your head and squint, you can see that this is really, if we let f of z equal to e to the pi z, this is f of z minus f of 2i, because 2 pi I is 1. So this is the difference quotient. And then we know how to differentiate that because we've worked out the calculus of the exponential, and as such, we get pi. So if you see a limit of a quotient and it's like, I don't know how to do this, odds are it's this trick. I don't know if I have really any other tricks like that in this class. I don't know. That's kind of the main one. Problem 15 was just the, here's your, it's our quick tour of our topological notions in here. We talked about open sets, closed sets, connected sets, star-shaped, and a domain was a connected open set. So connected just means you can, pick any 2 points, and you can, connect the points by a broken line segment, right? A bunch of line segments put together like that, right? Closed means that the boundary of the set is within the set. That's not the case here, right? Because it's got the fuzzy edge, so it's not closed. It is connected. It is open. Open means that if you pick any point in it, you can find a little neighborhood around the point which is still within the set. In terms of like intuitive calculation or thought, it doesn't have any solid edges. Star-shaped means that there's one point that every other point in it can be reached by a line segment which doesn't leave the set, no matter where you put the star center. If you put it like here, there's no way you can get to these points over here with a line segment that doesn't leave the set. So it's not star-shaped. But it is a domain because it's open and connected. So a domain is an open connected set. A region is a domain unioned with at least part of its boundary. Or I guess it doesn't have to have any, but a domain is a region. A region may or may not be a domain. But like a region is a domain where you've filled in at least part of the boundary, perhaps.
So if that was like one line, if that was one less than or equal, then it would be closed.
Right. Yeah. If we had if we had equality in the defining conditions, it would make it into closed. Okay. And if we just had equality on one side, it would be neither closed nor open. And it wouldn't be a domain anymore, but it would be a region. So, like the region doesn't, let's see what's this one here. F complex differentiable, show F as harmonic. This is a standard calculation. If we have the Cauchy-Riemann equations hold for the function, then we can differentiate the Cauchy-Riemann equations and show that fxx is equal to fyy a minus fyy, which gives us that Laplace's equation holds, which is to say that it's harmonic. You can also do it for u and for v separately. Like there's three options. Do it for u, or do it for v, or do it for f plus or u plus iv. I chose to do it at the level of complex notation. But well, I did ask to show f was harmonic here, so I really did need to do that. If I'd gone the path of real notation, I would have been obligated to show that uxx plus uyy equal to 0, that vxx plus vyy equal to 0, and then comment that, okay, so therefore f equal to u plus iv likewise has fxx equal to uxx plus ivxx, and fyy is equal to uyy plus ivyy, and therefore fxx plus fyy is equal to 0. And that just seems like a lot of talking. So instead, I just did it for complex. But anyway, the next one is to show that the level curves of u and v are orthogonal. The easiest way to do that, so you have to remember what's the geometry of curves, right? If we have this is u of xy equals to a constant, right? And we have that this is v of xy is equal to a constant. Then what are the gradient vector fields to those curves? What do they look like?
They have to be perpendicular.
Yeah, well, yes, these have to be perpendicular, but what do the gradient vector fields look like to these curves? I mean, they're just, I guess it depends on which direction u is increasing, but suppose u is increasing like that way, then the gradient vector fields are perpendicular. I think that's what you're telling me. They're perpendicular, right? So this is like a picture of grad u. And, oh, that marker smells like death. I'm not even joking. Golly, that's bad. And this one, would be the, gradient v. And so the first thing is to realize that if I want these two curves, to be orthogonal, right, then at a point of their intersection, it suffices to do what? To say, well, we need that the gradient of u, is perpendicular to the gradient of v. That's what we need. This will give us orthogonality. It's kind of the enemy of my enemy is my friend kind of deal, because the vector which is perpendicular to the level curve of u, you want that to be tangential to the v curve, but to be tangential to the v curve is to be perpendicular to the v gradient. But anyway, I think if you draw the picture, you can see it. And so what I calculate over here in the solution is simply that the dot product of the gradient vectors for u and v are, well, perpendicular, right? Like del u dot del v is this plus that. Cauchy-Riemann equation, 0. All right. And I let you choose your adventure here. So I hope that everybody would get this right, but I don't think everyone took the gift which I tried to freely offer. But anyway, this one was meant to be challenging in that I don't think I worked it in class. I'd worked problems like it, but not this problem. Like I think in class I worked maybe sine or cosine or sinh or cosh, one of them. So that one ends up involving a square root, I think. Well, it involves, the structure is just a little bit different for the sine, cosine, cosh, sinh ones. The tan and the tanh are a little bit easier actually, but they're a little bit different. So basically the game that you play is simply to write down the hyperbolic tangent in terms of the exponential and get rid of the fraction by multiplying by the denominator. And then you have to have the vision to see that you don't want e to the minus w. You want everything in terms of e to the w. Because you know that once you have e to the w, you solve for it, you can use the logarithm to solve for w. So multiplying by e to the w gives me this, which then if I collect all my e to the w's on one side, I got that. And so actually I get e to the w squared is equal to this. So I think in that sense, this is easier. Like the cosh and sinh or the sine and cosine one, you actually have to end up completing the square and actually going through the mechanics of solving the quadratic equation. But this one here, I just end up taking plus or minus the principal square root of that, which then using the little logarithm gives me that. I'm done. Now, actually figuring out the subset of the complex plane on which you can actually treat this function as a holomorphic function, that's a more challenging business. You see, that's a much harder question. Like, how do I choose a branch of this function which is holomorphic? You know, that's a harder question that I've asked in homework before, but anyway. So I just checked my answer here. This is like the other way to do it would be like calculus 1 style, because you can work out that the derivative of the inverse function has to satisfy this rule, 1/1 minus z squared, and so, yeah. And what was the question? Why am I doing that? Oh, and I forgot the last part of my problem, which was show that the derivative of inverse hyperbolic tangent is 1/1 minus z squared. So there's two ways to go here. The one is to use the formula which we just found for writing inverse hyperbolic tangent in terms of a log, right? In which case we just differentiate, use the derivative of the log as 1 over the thing times the derivative of the inside. So basically, property of the log and chain rule. But the other way to do it is to go back to like calc 1 style calculation and just calculate the derivative of inverse hyperbolic tangent directly to circumvent my whole derivation. That's like the other way. But no one's going to do it this other way because you guys don't remember this calculus 1 because either forgot or didn't learn it in your calculus 1 class. But that's okay. I mean, it is what it is. But
Is it good to have those identities for the hyperbolics like written on our note card?
yeah, I would say identities for hyperbolics are smart to write down because I don't see any difference between like sine, cosine, cosh, sinh. Like, I'm not trying to be vindictive when I put sine, sinh, or cosh in the problem. I just don't think of them as special functions. I think of them as just as normal as sine and cosine. So that's my, I mean, I don't, yes, in short, yes, it would be wise to put identities down. Better yet, like learn how to derive them all, you know. But it does help to have something for sure so you don't have time pressure to derive either, right? I mean, it's nice. Oh, and then here, that's just a follow-up, easy question. You already got the formula for inverse hyperbolic tangent, so use it. To solve for z, we take inverse hyperbolic tangent of both sides. And so inverse hyperbolic tangent of 2i is the solution, which is this, which works out to that as it happens. So there would be significant partial credit here for just writing z equals to, or maybe z is an element of inverse hyperbolic tangent of 2i. There's significant partial credit there. There's more credit to be earned by actually working out the details of that like I did there, though. All right, but take-home questions. Oh, why did I do that? I'm getting tired. All right. So here, what did I do? Reciprocal map, and we studied the image of a circle. I said graph at least 3 points. So reciprocal map is a very fun thing to think about graphically because like the way the reciprocal map works is if you feed it 0, it throws 0 to infinity. You know, and everything else, it just flips. Like the reciprocal map, what it does, sort of like globally speaking, is it takes the unit circle, it takes everything inside the unit circle and flips it outside the unit circle. It takes the unit circle and it kind of just twists it because it sends e to the I theta to e to the minus I theta. The reciprocal map does, like 1 over e to the I theta is e to the minus I theta. So it would take something at 45 degrees and reciprocates it down to minus 45 degrees. It takes something, you know, it does that. But it takes everything outside the unit circle and the reciprocal map folds it into the unit circle, right? It takes infinity and it maps it to 0 if we're working with the extended complex plane. So there's all that to kind of guide you in some sense. But notice that here we had the vertical line x equals to 1/2, right? So infinity is part of that. Like very far out, you think of that line goes to infinity. So if we're mapping that line under the reciprocal map, it has to go through 0. But on the flip side, you can pick, nice points like, well, it's especially nice to look at, I guess, I forget how I found these. 1/2 reciprocates to 2, right? So you got this point and that point around the circle. By the way, you also know it's a circle because the reciprocal map is an example of a Mobius transformation. And one of the things I told you guys was that a fractional linear transformation, something of the form like AZ plus B over CZ plus D, where AD minus BC is not equal to 0, is a composition of rotations, dilations, translations, and inversions. And all of those things map generalized circles to generalized circles. So like, if you feed it a circle, what's going to come out is either a line or a circle. If you feed it a line, what's going to come out is either a line or a circle. So we kind of have that as a backdrop. So I knew what I'm looking for here as I worked this problem. And it was a take-home, so like you ostensibly had all of the notes and discussion to bounce off of. And anyway, there's that one. Let's see here. So I define args of alpha to be, you pick the argument that ranges between alpha minus 2 pi and alpha in this case. Determine what choices of alpha allow for, well, I'm too tired to talk about this today, but that's an interesting problem. You guys should look at it. Oh, and here was just a build your favorite Mobius transformation question, right? So basically you just kind of, there are much harder versions of this question. But what I like for a test question is one that involves infinity, it involves 0, because those are really easy to track. Like if I'm mapping 0 to infinity, that means that the formula has to have division by 0 when you put in 0. That's what forces me to put this 1 over z over here. If I'm mapping 8i to 0, that means that the mapping must be 0 when I plug in 8i, which forces me to put a z minus 8i in the numerator. All that's left at that point is some multiplication in the front. And that's what the other piece of information, which maybe doesn't have to be so cool as these, gives you. And then you just have to plug it in and work it out. It turns out there it is. So, yeah. And then you remember we did this business where we looked at a solution in the W plane to Laplace's equation. And we can play these games with an argument times a number plus another number. And by shifting the value of A and B, we can force like minus 10 here and 10 up there using this kind of template solution. So this gives me this particular kind of solution in the W plane. And then the trick is I can use that to extrapolate a solution back in the Z plane by using this technique of conformal mapping is what this is. So like the thing is, this circle maps to that half plane under this map right here, T of Z. And I'm not sure why did I do that ZZ bar? Must have made, I'm trying to make the formula nicer, I guess. Oh, it's so I was trying to make it Cartesian, That's what I was doing. But, and the reason I'm doing that is so that once I find the Cartesian formula for T, I am identifying that as U plus IV that I'm sticking into the formula for psi, right? So in order to make this substitution, I have to understand the formula for T of Z nicely enough to identify what the real part and the imaginary part of the W that I'm plugging in are, okay, so that's why I'm doing what I did here. And so I identify this is my U, this is my V, and then since the context is that I'm in the right half plane, the argument is just the inverse tangent over there. So I'm able to just use inverse tangent of the quotient of V over U, which is this. And then after everything settles, you can study this solution and see that it makes sense. Like as you're going to the circle of radius 4 that's centered at 0, 4, that makes this equal to 16. You get division by 0. So you're getting division by a positive infinity for x positive, and you're getting division by a, I think a negative infinity for x negative. And so like inverse tangent of positive infinity is pi over 2. So pi over 2 times this gives us a 10 on the right half, and a minus 10 on the left half, which is what I wanted, I think, in the problem statement. So these are tricky. This is, I think, by far the most like sneaky thing we've done all semester. Like this is way harder than residue calculus, I think, because it involves substitution, mapping, geometry. A wise person would put this at the very end of the course rather than the middle, but I'm not that smart. I just put it in the middle because logically speaking, we had all the tools that we needed to do it. And also, I like to put something that's so demoralizing earlier in the course as opposed to right before the final, just as a point of not being too antagonistic at the end. But most complex books do delay that topic until like the bitter end, which is why a lot of like introductory complex variables classes won't actually get to it, because they're smarter than me and they have the good sense not to teach it. But didn't I say this was going to be a 20-minute review? What happened?
I'm fine with it.
You're fine with it? Okay, well, if you're fine with it, then I'll keep going. Although I'm imagining that some of the other students are going to be annoyed because I said I wasn't doing this. Which makes this all the more fun. The only way this could be more hilarious is if no one was here, you know? I have done that. Oh. I am my best.
You had a lecture with nobody.
Oh yeah, I've done that. I've done that on occasion. When you only, like in Alabama, I had 10 students across 4 classes. There's a very real possibility I would get to the classroom and there not be students. So sometimes you just have to just forge ahead, you know. The show must go on, with or without the audience, I guess. But I think I talked about this. I actually talked about this at the end of last class, after I got done talking about my fancy schmancy hyperbolic calculus stuff. But listen, this one really is just a straight calculation. Like, you just need to learn how do we calculate the complex integral, which is, it's the same thing we did in calculus 3. We parameterize the curve and we plug it in. That's really all there is to it. Like, z is equal to r e to the I theta. That's the parameterization of a circle. That would be a smart thing to have on your formula card, right? Like parameterization of a circle, parameterization of a line segment, right? Maybe like a case study on like the common contours, like the half circle, the keyhole contour. There's only like at most like 3 or 4 different common contours that we work with in here. And it would be smart to have each one of those in like an example, just a reminder of, we use this for this example, we use this for this example. That might be helpful. Not that I'm going to test all of the different contours on the final, probably not. Like, there's only so much time, But we do have 2 hours, so that does mean that sometimes I ask questions which are a little bit more, that require perhaps deeper introspection. Although that's less of an issue in here, because it's Tuesday, Thursday class. We got some time. I would say that's more of an issue. That has more teeth in the differential equations class. See, because in the differential equations class, I can ask a question on the final, which takes a half hour, that I wouldn't have asked in the in-class tests, because we just don't have enough time. If we were teaching Tuesday, Thursday, it'd be a different animal. So Monday, Wednesday, Friday is not a good fit for DiffyQ, unfortunately. I'm asking Dr. Joseph to try to not have it on Monday, Wednesday, Friday, if possible. I mean, it still works. It's just so many classes this semester in differential equations. I've been mid-thought, and I'm like, oh, end of class. Come back to it next class. Like, that's so, I guess, poor planning on my part. Anyway, this is just a straight calculation, like, Green's theorem. Would you have any questions about this test? I'm kind of run out of energy here. I'm kind of sick, and sometimes it catches up with me.
The solution to this test was great.
Yeah. Notice this one's a trap. Problem 4. You can't use the residue theorem here. You can only use the residue theorem if it's a closed curve. Or if you've got an indented contour, you can use the fractional residue theorem. There's those problems, but this one here, I wanted to tempt you guys to use the log, because an antiderivative of 1 over z is the log, right? Except when it's not, because the principal logarithm is not differentiable right there, because that's where the break is, the discontinuity in the principal log. So you have to use one of the other logs that doesn't have a jump in its angle on this curve. So I just use the log sub 0. And that matters because it informs what angle you put here and here, which does make a difference in the calculation. It's not a distinction without a difference. It matters. Let's see here. Problem 5 we did in class. Problem 6, you guys can everybody can do problem 6 on the final. Like a lot of people miss this on the test. And it's needless. Like, you guys can get this problem. You just got to be more careful and think through it. So we cube f of z's formula, and when we do that, that gets us 42 from that one and a 5 from this one, which gives us a 47. And then this right here is non-zero, so that means the 0 is order 47. Everybody can get that problem if I ask it again. You know, not that problem exactly, but you know. Now 7 was tricky. If you guys didn't get 7, I wouldn't feel too bad. Okay, so part of 7 everybody should get. Everybody should get this piece. This piece is easy, right? Integral around a circle. It's centered at 5. Its radius is 3. So you're going from 2 all the way over to 8. You got this circle of radius 3 like that, right? So both 5 and pi are within the circle, and as such, those are the residues that we face, because that's the places where our functions are divergent, right? So residue theorem says 2 pi I, sum of the residues. The residue for 38 over z minus 5 at 5 is obviously 38. The residue at z equals to pi of sine squared over 3z divided by z minus pi cubed is obviously 9. Okay, that's not obvious. It's not obvious at all, but it works out to be 9. And the way I did that, so some people were using the triple rule, the triple pole rule. That's not appropriate here, because sine cubed of 3 pi is 0. So you got a function which is 0 divided by a cube. You don't know. Well, you know for sure one thing. It's not a triple pole. It might be a double pole. It might be a single pole. It turns out this is actually a simple pole if we analyze the structure here, because like sine squared is that, and then I can, you know, do the I need to center it at pi, so I add and subtract pi to make it there, and then I use the Maclaurin expansion. The power series expansion for cosine is such the ones cancel, and it shows the true nature of the numerator is it's a 0 of order 2 at pi. So I've got a 0 of order 2 divided by a cubic 0 in the denominator. That leaves me with a simple pole overall. And so, yeah. And I mean, full disclosure, I meant to divide by 2 pi I here. This was supposed to be a 47. This one we've talked about. Like, we had homework problems like this, and some of you guys got it, some of you didn't. Everybody can get this problem if I ask it again. I oftentimes do ask this question. The basic issue is you can only use the geometric series result in the context which it is valid. And that context is that the ratio has to be less than 1 in magnitude. So like within the unit circle, my z squared being less than 1 is given to me because I'm within the unit circle, where the modulus of z is less than 1. Down here, I couldn't do that because it's not true, but what is true is that 1 over z is less than 1, which means that 1 over minus 1 over z squared modulus is also less than 1. So when I identify that as a ratio for the geometric series, I can do that, and there it is. So it's all geometric series and the geometric series convergent theorem. This one here is not hard. If you got it wrong, it's probably just because you didn't quite see the clockwise versus counterclockwise issue here, but that's most of what's going on at play. The other thing that's going on here is that to get from gamma r to gamma 2 and to get from gamma L to gamma 1, I'm using the deformation theorem. The deformation theorem says that the integral around 2 loops are equal, if the loops are oriented in the same way, and if the function is holomorphic between the loops. So we had that deformation theorem, which was a close cousin to like Cauchy's theorem. And then this was a homework problem. All right, so I'll let you guys look at this one. I don't want to say, I'm tired of talking about it. But this was a homework problem. And you guys found a better way to calculate the residue than I did. You just factored here and stuff. So that was good. And so it like I said, it was a homework problem. And this one was also a homework problem. But this one was trickier. Like this stopped me for a second when I was working my solution. I was like, how do I do this one? What's going on? What is this? And then I was like, oh, right. So it ends up after some calculation, and there's a kind of a sketchy, you'd be like, hey, you never proved you could do this, and I'm like, well, that's true. I didn't make you prove it either. So I trade this exponential, power series for the exponential, the integral of that for the series of the integrals. See that? Yeah, that little step right there I had to make. And it's okay because these are uniformly convergent series, which we did talk about. So it's not such a bad calculation, I suppose. But once you have that, then it's manifestly clear that you've got a zero. Okay, so like you could go to the rules, but it would be horrible. It would be kind of annoying. I don't know. How annoying is it? I don't know. Like you could use the pole of order n rule for calculating the residue. I don't remember that off the top of my head always. So when I'm faced with a problem like this, I'll go back to basics and just expand the function in a power series so that I can look at this and I can go, oh, okay, so, you know, to get the reciprocal power in z here, I need a z to the n upstairs, right? Z to the n divided by z to the n plus 1 gives me a net of 1 over z. That's the residue term. So the residue term happens when this over that matches up, which gives me a 1 over n factorial squared. So that's how I calculate the residue of that. And so, yeah. That problem, that's a problem. It's a problem. I like this problem, actually, but I think you got this one. Woohoo. But this one was pretty straightforward. You just go to the definition, use the fact that it's an antiderivative, use the chain rule, go back to fundamental theorem of calculus, and there it is. And this was the Cauchy's theorem proof. We did this in class. Here's, we might have done it in a different notation in class. I did it in the real notation this time. It's really just Cauchy-Riemann equations paired with Green's theorem. That's pretty much it. All right, let me see if I can find a final exam from yesteryear, just to give you a sense of, like, you know, what might happen. See if I can find one. What year do you want? 2018 is weird. Don't pick that one. 2023. 2023? All right. Let's see here. Wonder if I have a solution. That's the other thing. Well, I've got the final. It doesn't have solutions. You still want to look at it?
Yeah.
Okay.
There's one little bit of ways down.
Oh, is there one word?
The Math 331 submission. Oh no, that's a submission. No, yeah, it says the final underscore F23.
Oh, that one.
Yeah. I don't know.
Thank you. Excellent. Very helpful. All right. Let's take a gander. So, yeah, I had, so calculate the principal log, calculate I minus 1 to the 77th power. What else we got here? third roots of, that's I to the 1/3. I know the scanner's cut me off here mid-exponent, you know, but this is to the 1/3. So the 1/3 power has got 3 things in it, right? And I think I asked for the answers to be in Cartesian form, so that's why I'm going through the trouble. If I didn't ask for Cartesian form, like, you could stop right here, you know? I'm almost never content to have answers in the form like this. Like I do want, I usually either want a polar form or, you know, before that it's kind of unfinished in my opinion. I do realize that, you know, that kind of quibbling is a little bit like the high school teachers who force you to rationalize your denominator or something, but anyway, it's what I'm trying to teach in part in here. So, where is F holomorphic? So here's a look at the Cauchy-Riemann equations, analyze where they hold kind of problem. It happens this one is complex differentiable along y equals x. So it's nowhere holomorphic because there's no open set on which it's, yeah. Problem 3, find the Cartesian form of the solution z to the 4th equal to minus 28. So I use the 4th roots of minus 28 for my solution. There it is. Next problem was z squared analyze from the definition from Carr-Theodori. Or did I let you? Oh, I gave them a choice. Why did I do that? That was too nice. I should have made them do both. What's wrong with me? Oh, look, I saw, look at that. That's funny. I wonder how many people still got that wrong last year. That had to sting when you get it right and wrong the second time, right? He won't test that. That's too easy. He wouldn't put that on the final. Oh, yes, I would. Anyway. Suppose you got a holomorphic, prove it's harmonic. Okay, so yeah, this was a test question for you guys. Find the harmonic conjugate. So ux has to be equal to vy, so vy has to be 3y squared plus some constant function of x. But on the other hand, vx has to be minus uy, which gives me that the derivative of c1 has to be minus 6x, which tells me that c1 has to be minus 3x squared plus a constant, which gives me that v is this. And as such, if we put c2 equal to 0, we might notice that our function is actually just, well, this is z squared. So if we multiply that by minus 3i, we get back the u and the. So that shows you how I make up these. This is how I usually make these examples up. I pick some simple complex function like z squared, and I do something like, let's multiply it by 3i, or let's multiply it by 1 plus 2i, and then I let you find the harmonic conjugate of the real part of that. Because I know that it can be done, and then it's not too bad. And I also know that I'm pretty much safe from students guessing it, because most students can't just like eyeball it and go, oh, this is just 1 plus 2i times z squared. Cook, he's up to his old tricks again. No, it doesn't happen. I mean, it could happen. That student could arise. So here I asked to find the component functions. For this, gift. For this, not quite so giving, but you can do it. You just need to know your trigonometry and what your goal is, right? There's not a unique answer. Like there's a way of writing this in terms of other functions, but anyway, there's how I did it.
That was from the first test, right?
Yeah, I think so. Find all the solutions of sinh of iz squared minus 1 equal to 0. This is a nice problem. So what I did is I converted this to a sign problem. The reason I did that is because we've already solved the sign problem in class. We know that the only solution to sign of a complex quantity equal to 0 is that the complex quantity must be an integer multiple of pi. So that gives me that z squared plus I is equal to n pi, which then I can solve for z is plus or minus the square root of n pi minus I. You notice here I've been hypocritical. I haven't rewritten this in terms of its real and imaginary parts. You'll forgive me. But the reason for that is it's not particularly enlightening to dive into the substructure here. You know, like the magnitude of this is the square root of n squared pi squared plus 1. Great. And the angle is complicated. Like maybe it's not too complicated. Maybe I'm wrong. You know what? I probably could have written this as the square root of n squared pi squared plus 1 times the inverse tangent of 1 over n pi. Maybe I could have done better there, actually. Maybe you could improve on that answer. But these aren't really intended for publication. I just write these solutions for myself, you know, because I don't pass finals back. Complex differentiable, prove it continuous. So easiest way is with Carathéodory. You just take the limit of the function, which is the limit of the function, its value at z naught plus the Carathéodory function times z minus z naught, which immediately leads us back to z f of z naught. Prove the product rule. Here's actually the proof of it. That was also a test question. You're noticing a theme here. Let's see here. Find a fractional linear transformation f of z equal to blah, 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 for which f of 0 is infinity, f of 1 plus I, f of 2i is equal to 0. So I just, with like a laser focus, go, infinity, 0, use those. So if I want 0 to go to infinity, I divide by z. And I want 2i to go to 0, I put a z minus 2i upstairs. And then this one will fix the value of a, like so. That gives me this function. And then I say explain where the disk z minus I less than or equal to 1 is mapped to under f of z. So there, that you can figure that out because the way a complex differentiable map works is it maps interior to interior. And this is a Mobius transformation, a fractional linear transformation. So it maps a circle to either a circle or a line. But it's a circle through the origin, and this involves the division by z, so that means it's mapping it to infinity, which means this is it's coming out with a line. It has to map to a line. So once I figure that out, I'm like, oh, it's a line. And I just need to pick some points on this circle. I think I picked this point, this point, and this point, fed them into this, and got this, and infinity, at which point it becomes clear. And then you have to think about the orientation. So if I start here, then here, then here, then as I walk around it, this is the inside. And correspondingly, if I'm here to, well, I walk from here to here to here, that's what this arrow is, the orientation of the boundary. This is oriented this way, that's oriented that way, following point to point to point. And so as I walk down, that's on my left. So the inside of this gets mapped to the right of that, is the point. As you can tell from all the hand waving, it must be correct. Then, so this is just launching off what we just did to, solve Laplace's equation in the disk by stealing Laplace's equation, Laplace's solution of Laplace's equation on the half plane. This is the conformal mapping idea again. We move on here. And let's see here. Oh, goodness. I'm going to try to speed up a bit. So here we just have a direct from the definition calculation for the integral. And then use the FTC for line integrals calculation. You see the difference there? From the definition, I parameterize the curve, and I actually do the real integral from 0 to pi over 2 for the half circle, right? FTC, I find the antiderivative, and I simply evaluate at the endpoints. And of course, we should get that they're equal, right? I tried to do that for you guys on the last test, but you just like slopped through the second part and then made your wrong answers match up, and that kind of defeats the whole purpose of having like a redundant check pair of parts in a problem, but you do what you do. This one here, let's see here, calculate by appropriate theorem. This one I can, okay, so this one I've got a divergence at I inside the circle. And the log is fine. It's got trouble over here, but over here is outside the circle, so we don't have any issues with that. We can just use the residue theorem. Yay, and we do that, we get that. This one here, the circle is still the same thing. The thing is, that circle, it does not have 1 in it. 1 is over here. So this 1 is outside the circle. So the fact that this blows up matters not to us. this function is simply holomorphic on the circle, so the integral is 0 by Cauchy's theorem.